Hello and welcome to another Common Core Geometry lesson by eMathInstruction. My name is Kirk Weiler, and today we'll be doing Unit 7, Lesson 7 on more similarity reasoning. So in the last lesson and on the last homework, you worked some on doing proofs that involve similarity, and oftentimes those proofs involve proving two triangles were similar by using the angle-angle similarity theorem. Today we're going to do very much the same thing, but kind of add one additional step. And the reason for this is that later on in the course, especially when we start to work with the geometry of the circle, we will need this type of reasoning to prove many of the important theorems about circles and their geometry. First though, let's review something from a long time ago. So, a long time ago, in a place I like to call 5th grade, you were learning a lot about fractions and equivalent fractions and how to tell whether fractions were equivalent. And we're going to sort of use one of those tests today, all right, to start off the lesson. And I know this seems kind of strange, but let's take a look at what exercise 1 asks us to do. Exercise number 1, test the truth of each of the following fractional equations by seeing if the products of the means is equal to the products of the extremes. Show the product and then write true or false. All right, so back in 5th grade, and still in high school, you probably use this. To test whether or not two fractions were equivalent, 3/6 and 1/3, what you would do is you would find the product of these two numbers and see if it was equal to the product of these two numbers. All right? And we'll talk about this whole means and extremes thing in a moment, and which one are the means and which ones are the extremes. But quite frankly, it's a little bit irrelevant. When we do this problem, we of course see that 3 times 3 is 9 and 6 times 1 is 6. And obviously 9 doesn't equal 6. So false. And what this tells you is it tells you that 3/6 and 1/3 aren't equal fractions. Now if you're sitting around saying, well, I knew that 3/6 was 1/2, so I don't need to do this, I completely agree with you. It's not that. It's the fact that we can always take a fractional equation and rewrite it as an equation that involves a product. And if the original equation was true, the product will also be true. So what I'd like you to do is take a moment now, pause the video, and test the truth or falsehood of these two equalities. All right, let's go through them. So in the second one, right, what we're looking at is whether or not 4 times 15 is equal to 5 times 12. All right, and what we find is that 4 times 15 is 60, 5 times 12 is 60, so that's true. And again, the idea here is very important, which is that what this means is that because this is true, this is true. And likewise, because this is true, this is true. All right, 4/5 and 12/15 are the same. And you can, of course, use some kind of a reduction technique, like saying, well, if I take 12/15 and I divide both numerator and denominator by 3, I would get that 4/5. But, again, if I've got a fractional equation that's true, this product will also be true. Likewise, for this last one, if I do 7 times 15 and see if that's equal to 3 times 35. This might be a little bit more difficult, but we would have 105 here, and likewise we'd have 105 here. So that is true as well. All right. If a fractional equation is true, if one fraction equals another fraction is true, then when we do the products of the extremes, we'll get the products of the means. So let's talk about that a little bit more formally. Okay? Now again, it's not very important, actually, it's not really important at all, that you know which two are the extremes and which two are the means. Those terms get wrapped up in what are called geometric means, and some of your teachers might even talk to you about what a geometric mean is. It's a different way of finding an average of two numbers, all right? But regardless of all of that, if you've got two fractions equal to each other, all right, then the number up here and down here are what are called the extremes, and the number here and the number here are called the means. And the idea is, if we know this is true, then we can always rewrite it in terms of a product, And the reason for that is that the product of the means is equal to the product of the extremes. Okay? And that's going to be a reason that comes up in proof. In fact, it's going to come up in the next problem. So let's take a look at that. All right, here we go. So back to geometry. Not so much forgetting about fractions because we're going to end up having some fractions in here, but let's take a look at exercise number 2. In the diagram below, AD and BE intersect as C. As well, AB is parallel to ED. Letter A asks us to mark all angles that are of equal measure in this diagram based on the givens. So what I'd like you to do is take a moment and use kind of those single arc, double arc, triple arc marks and mark every single angle that you know, or every angle pair that you know is equal in this problem. All right, let's go through them. Well, there's a variety of different ones we can do, but I know that this angle, angle A, is congruent to angle D. All right, they're alternate interior angles formed by two parallel lines. Likewise, I know angle B is equal to angle E. Again, alternate interior angles created by parallel lines. And finally, even though it really wasn't in the given, well, it kind of is in this given, AD and BE intersect at C. We also know that this angle is congruent to this angle. All right? Now, the reason that it's nice to have all those congruent angles marked is that at this point, of course, you have a very, very good sense that these two triangles are similar. Let's talk about that in letter B. It says, which two triangles are similar? How do we know? Write down a similarity statement below. Watch the order of your vertices. It's helpful to redraw the two triangles. All right? So there's only two triangles in the picture, and that's triangle ABC and triangle DEC. Okay? But why do we know that these two triangles are similar? Right? Well, let's take a look at their pictures drawn separately, right? So what I've done is I've taken sort of that larger triangle that's up here, and I've flipped it down here, and I've tried to draw them in what's known as the same orientation, okay? And I do this so that it's going to help me think about those similarity ratios later, okay? But what I see is that A corresponds to D, B corresponds to E, and C corresponds to C. So I can say that triangle ABC is similar to triangle DEC by the angle theorem. Now you might say, well, I've got the angle theorem. Now, one of those three angle pairs is somewhat redundant. All we need is 2 out of the 3. But what's nice about having all 3 of them marked is then we can truly see the sort of orientation of the two triangles, the two similar triangles. Two triangles that have the same shape, but different sizes. Now, the last part of the problem is sort of a mini proof, and it's one of those proofs where I've given you the statements, and I ask that you fill in the reasons. So let's actually take a look at this together. All right, then the next one we'll kind of talk about it and let you work on it some on your own. But remember, at this point, I know that these two triangles are similar, okay? And they're similar by angle. I don't have any side information here that I can bring in. So why can I say that BC divided by CE is equal to AB divided by ED? What allows me to set up that proportion? What is the reason for it? Well, what I'm going to state pretty much every time in one of these proofs, just like in the last lesson, is I'm going to say that corresponding sides of similar triangles are proportional, right? These two sides, BC and CE, are corresponding, right? They're kind of between the two angles that are marked the same, right? And therefore, if I divide them, right, BC divided by CE, then I should get the same thing as I got if I did AB divided by ED. Side note, it would be the same thing I also got if I did AC divided by CD, but that's not part of this proof. Now I take this equation and I rearrange it. I rearrange it as CE times AB is equal to BC times ED. And the reason that I'm going to always put 100% of the time when I take a fractional equation and I rearrange it into a product is that the product of the means is equal to the product of the extremes. Now, side note, If you said the product of the extremes was equal to the product of the means, awesome. If you have this product written sort of the other way around and you still said the product of the means is equal to the product of the extremes, still okay, all right? The idea though is that you have to have a reason, or you have to be able to give a reason why you can rearrange a proportion into a product, and the standard reason that's accepted is the product of the means is equal to the product of the extremes. It's a little bit annoying, but we'll see it quite a bit as we move on in this course. So let's do now a real proof. All right, now it's not overly difficult, but let's take a look at the setup. Exercise number 3. In the diagram below, points N and P are located on sides MQ and MR such that NP is parallel to QR. All right, so I've got these two parallel line segments. Okay, now notice what it asks me to prove. Just based on that parallelism, I'm asked to prove that Mn times Mr, make sure that you can picture it, Mn times Mr is equal to Mq times Mp. If you see a statement like this in terms of what you're supposed to prove, it is a huge red flag that you're using similar triangles. It's very similar, no pun intended, it's very similar to when we did CP-CTC proofs, right? When we were told to prove that this side was congruent to this side or this angle was congruent to that angle. That was a red flag of we probably are going to have to use CP-CTC reasoning. This is an even bigger red flag. I pretty much guarantee you, in a geometry proof, if you're asked to prove that one product is equal to another product, what you've got to do then is to prove that two triangles are similar. Now the two triangles in this case are triangle MNP. So let's talk a little bit strategy. We need to show that triangle MNP is similar to triangle MQR. So sort of the smaller triangle embedded in the larger triangle, those two triangles are similar. All right, that's what we have to do. Once we have those two triangles similar, we can then set up a proportion that involves these four sides. Okay, and that's not going to be actually all that hard to do, but we first got to get the triangles similar to each other. And so that we can all sort of follow along on the same proof, one thing I'm going to do is I'm going to label those two angles, angle 1 and angle 2. Just kind of what I'm going to do. Okay, so taking it from there, see if you can first do a proof that just lays out why these two triangles are congruent. Go ahead and do that. If you want to label more angles with numbers, that's okay as well. All right, proof is kind of up to you, and then we'll take it from there. So take a few minutes. All right, let's go through them. So here we go. First, I just want to establish this similarity, and that's pretty easy. I start with my pretty much one and only given that NP is parallel to QR, and that's given. All right. What can I immediately get from that? Well, I can get the fact that those two angles that I've numbered are equal to each other or congruent to each other. And that wordy kind of congruent statement. Corresponding angles formed when parallel lines are crossed by a transversal are congruent. Now, if you're kind of heads up and you want to save yourself a little bit of space, you could have also easily labeled this angle 3 and this angle 4 and also claimed that those two were congruent for exactly the same reason. That's fine. I wanted to mix it up a little bit and get a different reason in there. I'm going to say angle M is congruent to itself, right? Keep in mind that angle M up here is part of NNP, but it's also part of MQR. And anytime an angle is shared between two triangles, you can use it as a pair of angles that are congruent to each other. The reason, though, of course, isn't shared angle, but the reflexive property. Now we've got two pairs of angles that are congruent to one another. One is congruent to 2, M is congruent to M. So I can now say triangle MNP is similar to triangle MQR by the angle-angle similarity theorem. So let's pause for a moment, right? We've got all of that. Now what I need to do is I need to get things, some kind of proportion down. I can't go right for the final answer. I've got to get a proportion down that involves side MN, side MR, right? So I've got side MN I need in here, right? I've got side MR I need in here. I've got side MQ, so I need to get this thing involved, and side MP. Notice the two sides that aren't involved, because quite frankly, between two triangles, of course, there are only 3 side pairs. The ones that aren't in this proof, they could have been in this proof, they're just not, are those sort of parallel sides, NP and QR, NP and QR. Those aren't there, all right? Now, we could set up a variety of different proportions that involve those 4 sides, the 4 that I've marked. Every single one of them would lead to this. Every single one of them would be sort of an equivalent proportion, all right? What I decided to go with was the following. MQ divided by MN is equal to MR divided by MP. In other words, I decided to say, well, if I take the long side of the bigger triangle and divide it by the long side of that smaller triangle, then I'll get the long side of the bigger triangle over, or sort of this side of the bigger triangle divided by this side of the smaller triangle. They're the corresponding sides, right? So again, just stepping out of the way, MQ divided by MN is equal to MR divided by MP. So large divided by small, large divided by small in terms of the triangles. And the reason for that, corresponding sides of similar triangles are proportional. And now the beautiful thing is I can now say, all right, I'm just going to rewrite that as a product statement. Even if you had written this on the left-hand side, whoops, even if you had written this portion on the left-hand side and this portion on the right-hand side, you'd be okay, as long as you then said the product of the means equals the product of the extremes. So we're really adding one additional step to the proof that we didn't have in the last lesson. Now that may seem overkill for a single lesson, but keep in mind, right, it would have been probably too complicated in the last lesson to have this, all right? Product of the means equals the product of the extremes. Take a minute now and copy down anything you need to in this proof, right? Look at your own proof. If you wrote one that was slightly different, it still could be very, very correct depending on sort of what you were doing up here. So take a minute and write down anything you need to. All right, let's move on. So, one of the things that we're going to be working with in a future lesson are right triangles that also happen to be similar. And one of the very strange things that happens is that when you take a large right triangle, like this, and you draw an altitude, remember an altitude is simply a line segment from one vertex perpendicular to the opposite side, so BD here is an altitude. Then what happens is you get similar triangles. And we're going to look at that. We're going to devote an entire lesson to it. But I want to start to get into the thinking of it today. So let's take a look. Exercise number 4. Given triangle ABC with right angle, angle ABC, the altitude has been drawn to the hypotenuse, AC, and terminates at point D. Great. Letter A. Explain why ADB, triangle ADB, must be similar to triangle ABC. So why does this triangle up here, ADB, why does that have to be similar to triangle ABC? I want you to pause the video now and see if you can just come up with a little paragraph proof kind of proof. It should be very, very short. Yes, a paragraph proof. A little redundant. Let's take a look. All right. Well, in order to get two triangles similar to each other, what we really want to have is two angle pairs that are congruent. Well, one thing that is certain is that angle ADB is congruent to angle ABC because both are right angles. All right. So we're halfway there, right? We need to get two pairs of angles. Here's pair number 1, all right? But here's the beautiful thing. Angle A is shared between the two. Right? Angle A is shared between the two, right? Both ABC has this angle A and ADB has this angle A. And because of that, they must be similar by the angle-angle theorem. Right? Ooh, there's my red pen. Awesome. So that's it. Right, you could also make the argument, we're not going to right now, but we will in a future lesson, that this other right triangle down here, BDC, right, because that would also be a right triangle, BDC will also be similar to ABC. And then the cool thing is, if this is similar to the large one and this is similar to the large one, well, then they have to be similar to each other. There are three similar right triangles in this picture, and there always will be when the altitude is drawn from the right angle to the hypotenuse. Again, a whole lesson on that later. We're just starting to get our thinking on here. Now let's take a look at letter B. It says draw a triangle ADB, the smaller one, ADB, below triangle ABC so that it's in the same orientation as ABC. All right, let's talk about this. This is going to be very important, especially when we do the lesson that's just devoted to this stuff. In every right triangle, except for a isosceles right triangle, you have a shorter leg, a longer leg, and the hypotenuse. Shorter leg, longer leg, hypotenuse. In this particular picture, just concentrating on the large right triangle, ABC, AB is the shorter leg, obviously, BC is the longer leg, and then AC is the hypotenuse. In this triangle ADB, it should be pretty obvious that AD is the shorter leg, BD is the longer leg, and AB is the hypotenuse. So if I want to draw these two triangles in the same orientation, then I want to have ADB drawn like this. Okay, I want to have it drawn like that. And again, it kind of makes sense that I want to have D down here because it's the right angle and it should be in the same place B is. Okay, because B is the right angle in the larger triangle. A is a shared angle, so it should really kind of be in the same place. Now the beautiful thing about having this triangle and this triangle sitting like this is that now I should be able to set up ratios very, very easily. And in fact, let's take a look at letter C. Letter C asks us to give a short proof for why AB squared is equal to AC times AD. All right, and again, notice what this really is. We're trying to prove some kind of product equal to a product. We've already proven up here that the two triangles are similar by angle-angle, so we don't need to do that again, all right? We just need to take it from here. So see if you can fill in some statements and reasons down here. You could do it in a T-table proof if you wanted to, or you could just kind of do a paragraph proof. Either way, take a little bit of time with it. All right, let's go through it. So let's take a look at what we want. We want to get side AB involved. I'm going to circle it here and I'm going to circle it here. We want to get side AC involved, all right, which is my long hypotenuse here. And I want to get AD involved, all right. So it looks like the two sides that aren't involved in this particular product are BC and BD, right? Not this one, not this one. So let's just set up a proportion involving this side, this side, this side, and this side, right? And what I can say, many different versions, whoops, is I can say that AB divided by AD, right? So AB divided by AD is equal to AC divided by AB. All right, and the reason for that is corresponding side pairs in similar triangles are proportional. All right, and then the beautiful thing is I can then write this as AB times AB is equal to AC times AD. And of course, for that, I will say the product of the means equals the product of the extremes. All right. Now, of course, it's a little bit different than this, but not really. AB squared is AB times AB anyway, so we can just leave it at that. All right, that's the whole deal. So let's wrap this up. Let me give you a moment, though, to copy down anything here you need to. Maybe pan up a bit. There we go. Now you can see the whole problem. All right, let's wrap up. So today, we literally added just one little twist over our last lesson, okay? Which was if we're asked to prove some kind of a product equality, this product is equal to this product, then what is the reasoning behind that? And the reasoning behind it is that the product of the means is equal to the product of the extremes. Or you could easily say the product of the extremes is equal to the product of the means. It really doesn't matter. Probably more important than that, though, is just the idea that if you see that as part of a proof, it is a huge red flag that what you're trying to do is use similarity to establish that two triangles are similar, right? Probably angle, angle. Then from that similarity, you're then looking to set up a proportion, this side divided by this side is equal to this side divided by that side. That we did in the last lesson, but then that final piece is rewriting those proportions as products, okay? And that will be very, very important, especially in Unit 9 on circle geometry. For right now, though, I'd like to just thank you for joining me for another Common Core Geometry lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.